as I must say n goes to infinity. As n goes to infinity. Maybe I'm too quick. So I'm saying keep an eye on this interval. Keep a very, what do you call it, strict eye on this interval. So what would be the value of the process, here? So it's going to be this, for example. Okay? And I'm saying forget about all other intervals. Alright? And I'm breaking this. But increasing the n. Okay? So what would be the value here? So it's going to be close to this previous point. So what would be the value here? So it's going to be this, because this point is a, this point is a, okay. So let me just give this. Just imagine this is a zoomed picture actually, okay? And you have this interval. So this point is a right end point of a previous interval, so its value is this. And this point is a right end point of this, so its value is, for example, this. And I'm saying break it down. So its value is going to be this. I'm saying break it down. So this value is going to be this. And I'm saying break it down. Can you see what is happening? So in other words, so you can fill this roughly, you can say, this line with the dots actually. So I'm going to say, you keep on increasing the dots, you keep on increasing the interval, the more and more dots will appear, and those sequence of the dots, the process of the dots is going to converge to the original function. So that's what is argument actually. That's what is argument. Okay?
Sir, constant वाली बात को एक बात
convergence with respect to first argument.
Point-wise convergence with respect to
First S.
yes, obviously. Point-wise convergence with respect to the time actually. Okay, so this convergence so omega is fixed. You may assume that. Okay, since because I assumed actually since I have taken one particular trajectory, so this means omega is fixed. So you are seeing it as a function of time actually. So everything is varying over the time. So omega is not varying. So obviously everything is happening with respect to that time.
सर दो बातें अभी कंफ्यूज करें एक कांस्टेंट वाले थोड़ा और दूसरे जो कांस्टेंट क्यों है ये मतलब
वो ये तो बड़ा मुश्किल सवाल है. You have to think for yourself. Constant.
चलिए ठीक है सर वो assumption जो
are constants random variables?
Yes sir, measurable.
Each random variable is measurable.
नहीं वो ठीक है मैं क्या ये constant क्यों है सर वो आप
ये constant क्यों है? Because think about it. So I am saying take a subinterval.
सही सर.
Okay, take a subinterval and take an s from here.
सही सर.
So take this as s. Okay. So what would be the value of the process at this s is going to be this dot. So if you take another s, what would be the value? The value would be always same actually. For this entire interval value is same.
सही.
So it's fixed over each subinterval. Okay.
So this process is not discrete process, right?
Which one?
The xn one.
It is discrete. It is discrete.
Sir, what do you mean by discrete process? Does it the inputs are discrete or the output is discrete? Here inputs are, sir, on the real line.
Inputs are on
Real line. They're not in jumps in discrete process.
okay. Or you can treat this as the other way to look at it is you can treat it as a step process actually.
Yes.
This is a step process. If this makes a bit life miserable, then you can treat it as a step process. Okay? Anyway, just try to give you a bigger picture of it. Okay? So what does this result says that if you have a process which is path continuous, which is Brownian motion is indeed path continuous, okay? So it must be progressively measurable. So the Brownian motion is progressively measurable. Okay? You can read it more as well. And you can correct me. Maybe I have took it. Okay. Okay. So instead of dots, it's going to be lines actually. So in other words, if you have this interval, so it's going to be this line.
Yes.
As a value. But I'm saying if you make it smaller, it's going to be.
The lines are,
this line.
approximating to it.
Yeah. But you will see that these lines will shrink in their size and almost become dots, and dots, you combine the dots and you get the curve actually. That's what you do. Okay. Maybe my intuition was, my picture was not 100% correct, but almost there. Okay. So we got it to the collective wisdom. Alright. Here is a little remark. So you will see progressively measurability in stochastic literature appears a lot. And why? Because it makes your life easy. Okay? Because if you have adaptedness, you can apply many results actually. Okay? Every single result requires measurability. Imagine you have some function that you have to deal that is not measurable. I mean, you can't do anything with it actually. You can't define integrals, you can't, there are lots of things which you can't apply. There are lots of measures that you can't apply actually. Okay? So if you have measurability, obviously you can do a lot of things. Okay? Here you have progressive measurability. So progressive measurability assumption help us a lot. There is another thing which you will quite often see in stochastic analysis is you will see a probability space which says omega f p and a filtration over time. Okay? And you will hear satisfies usual conditions. Okay? Usual condition. Now the usual condition is a technical word here. It's not a. It has a definition behind it actually. Okay. Now you will also see a lot of stochastic analysis is being done. Most of the stochastic analysis is being done in the probability spaces which satisfy the usual conditions. Okay, because it makes your life easy. Okay, it makes your life easy. So what do you mean by a probability space satisfy the usual conditions? So first thing is obvious that it should be a probability space. So there are some special things that are satisfied this filtration actually. Okay, and what are those things? This is following that. So if I call f infinity, okay, as a sigma field, it's a cumulative sigma field generated by all ft's, where t could be anything. You can say t is in the time interval t. Okay, it should be finite, it should be infinite. So by f infinity, I'm going to mean the sigma field generated by all sigma fields. Okay. So the first condition that this filtration must satisfy that all subsets of p null sets in f infinity are members of f naught. Okay? All members of f naught. I mean, if I give you a rough analog, what you are assuming is that your measure space analog, so your measure space is complete actually. So in other words, it contains all null sets actually, okay, under that measure. So if I say more precisely, all those subsets, null sets in the F infinity. So all those subsets whose measure is 0 under the probability measure V, but those subsets are the subsets of the sets in infinity, they are also in F naught actually. Okay? So if I write it precisely, how does it go? So you're going to say, if I take A, that is from F infinity, okay, and I take a B, that is the subset of A, such that the probability of
Probability of A is 0.
the probability of A is 0. I should say that then. So have A in infinity such that probability of A
0.
is 0.
B is subset of
Now
A.
for any B,
Then any B
Subset of A.
that is subset of A implies that B must be
And F naught.
F naught. Okay? It's like making your filtration complete. You just go back and remind the definition of complete matrix space. Roughly, you also have a separate definition that there must be all
Null sets contained.
and the zero measurable set, so it contains basically all subsets as well, which have measurable. Okay. That is one of the things. And the filtration FT, this filtration FT, T is in T is right continuous actually. Okay. Right continuous. That is for all non-negative T. Okay. Ft can be seen as the intersection of all FU's such that those U's are smaller than T. So U bigger than T. So the filtration of the right continuous. Okay. So what does this say? That Ft can be seen as the intersection of all sigma fields at instants U which are coming after the T. Anyway, so in the stochastic analysis literature you will see, all papers starts with this actually. So imagine you have a filtration that satisfies usual condition. That means there is huge amount of literature that you can access now. Okay, you don't have to worry about the tiny things actually. The Lagrange map, is it measurable? Would be always measurable. Okay. A lot of analysis. So progressive measurability and usual conditions, these are the two common things that you always quite often see in your stochastic analysis literature. Okay? Alright. So I'm just quoting some properties, and I'll just give you a rough sketch of the proof, not the complete proof. You have to read it for yourself discreetly. Consider you have 4 instances, 0, s less than or equal to t and less than u. Okay, and consider the increment actually, wu minus wt, where w is obviously ground in motion. Then this increment is independent of
T minus S.
previous increments, not only previous increments, but all this information that you have up to the time t actually. So the sigma field generated by, okay, so let me write it. So that this increment is independent of, okay, of sigma field that is generated by Ws for all s less than or equal to t and t. Obviously s must be 0. Okay? In other words, we know increment here is independent of increment here, but this gives you an extra layer of information that not only this increment is independent of increment here, but everything that you can make out of, everything that you're going to do with this interval is going to be basically independent of it. Okay? So none of this information up to the time t is going to add anything into, is not going to put an impact here. Okay, so this is what is for. Okay, and there is a symbol for it. So what was the symbol that we said for it? You can put a symbol, so it's a calligraphic S, and calligraphic D. I should say W of R, and R is less than or equal to S. Let me write it. So it's independent of Fs generated by W, which is the sigma field generated by WR, all information, okay, that you have up to the time Sf. So not only increment, but all information that you have up to the time Sf. All right. Why this would be the case? Why this would be the case? One thing is intuitively look okay. Okay, it's intuitively looks okay. But how can I say it precisely? How should I say it precisely? So the way to say precisely is going to be, so first observe that WU minus WT, so the sketch of the proof is this, WU minus WT and WR minus W0, okay, where R can be anything up to S, okay, are independent. Okay. So how can I say now that the sigma field generated by this increment, so this is also going to be independent of the sigma field generated by this. Can you quote a result? We did this in measure theory. We said, imagine I have two random variables x and y that are independent. Okay? Then x is also going to be the sigma field generated by the random variable y. Okay? So if these are independent, okay, this implies.
So is it both ways?
This both way, obviously. It's both way. If x and y are independent, in other words, you can say the sigma fields that are generated by x and y are independent actually. Okay? But this would be a more stronger assumption. But I can say that x and the sigma field generated by y are independent. What is the precise meaning of it? What is the precise meaning of x and a sigma field, a random variable and a sigma field generated are independent?
Any set from this.
Any set from.
So you can pick any set from here, A, and pick any Borel measurable and consider its inverse image, okay, and compute their probabilities.
They are.
So the probabilities of the intersection is the
Product of the
product of the probabilities. That's what it means. Now I'm saying this is like your x, and this is like your y. And this fs is the sigma field generated by this random variable. So if these two are independent like this, then the same result tells you that this would also be independent of
sigma
the entire sigma field that is generated by this. Okay? So read more and more read. Okay? This precision is key thing, okay? Things are abstract, but once you have this precision, once you keep the results in mind, it helps you a lot. Okay? I can't just get into every single detail and keep it. Okay. Martingale in continuous time. So when a continuous time stochastic process is martingale, so what do you think, what should be the definition? So process x t where t is from the time is martingale, okay, with respect to the filtration ft where t is in t, okay, which will only what happens, give me the definition. So you should say that x is adapted to the filtration of St and must be integrable. So integrability means that if you compute the absolute of xt, it must be finite. And the third thing should be that if you compute the conditional expectation, and obviously if I say more precisely, this must happen almost surely. Okay, and the expectation of xt given, you have sigma field fs. You have to keep in view, this sigma field is not necessarily generated by the process act. It could be any sigma field.
It's not natural.
Yeah, it could be any sigma field. So should be equal to
Excess.
So we have this definition.
It should be less than t.
Okay, you can say s is less than or equal to. And obviously this must be true, be almost sure. Okay? So that's a definition. Really analog to what we have in continuous time. There are 3 examples that I'm going to talk. Not I'm going to talk, I'm just going to do one and you have to for rest. Find yourself. So, think in your head, is Brownian motion a martingale?
Expectation
Should it be martingale?
expectation 0 thus equivalent.
Why it shouldn't be? It should be. Okay, so here the proposition which says that if you have Brownian motion in a process greater than or equal to 0, and you have the filtration generated by the Brownian motion. Okay, so whenever I'm gonna put up, for example, process here, I mean a filtration generated by, so natural filtration to the, okay? So imagine you have 2, then Brownian motion and square of Brownian motion minus t, okay, and exponential of sigma. There can be many examples. Okay, you'll find some of them in exercises. T minus sigma square over t. T are martingales. They are examples of martingales. So Brownian motion itself is martingale, and this is the function of Brownian motion. So it's also martingale. Function of Brownian motion, that's also martingale. And you will also see other functions of the Brownian motion that are martingale. You may choose one. So which one should I show you then? First one?
Last one.
Why the last one? Difficult. Let's do the middle one. Why this process is adapted to FT. So FT contains the all information about the Brownian motion up to the time t.
Generated.
So if you have, for example, a Borel measurable function, okay. So in other words, this is a nice function depending on, Brownian motion. So this would also be measurable with respect to FT. Okay. So it shouldn't be a trouble. Maybe you can think of a result that justifies it, that why this is measurable. Okay? Because we did one result that if you have a continuous map and you compose it with a more Borel measurable map, their composition is also Borel measurable or measurable. Sorry. Okay? So I have a continuous I have a measurable map. I should say correctly. I have a measurable map. So WT is measurable.
X square.
And you take a Borel measurable map. So continuity is an example of Borel measurability. Okay? So I have a Borel measurable map, and I compose that Borel measurable map with a measurable map. The output is also measurable. Okay? So we did one similar result actually. Maybe a bit imprecise in description, but we can get back and have a look at that. So measurability is not an issue. Okay? Measurability not an issue. So what expectation is easy to calculate. Okay, not a big deal. So what would be, so is it integrable?